Hello, I'm Gyuwon Jung, a PhD student at School of Computing, KAIST. In this presentation, I'm going to introduce DeepStress, supporting stressful context sense-making in personal informatics systems using a quasi-experimental approach. Personal informatics has become prevalent in our daily lives due to the widespread use of smart devices. These systems assist users in gathering personally relevant information, enabling them to reflect on their past self-tracking data and gain insights into themselves. Existing HCI studies have proposed personal informatics systems targeting various health and well-being domains, focusing on physical and mental health issues that require long-term management for optimal care. In personal informatics systems, users can analyze correlations within their self-tracking data. Among various data-driven insights, relationships between different factors is critical because users can investigate what affects their health status. Regarding this, previous studies have suggested systems that support correlational analysis between diverse factors. However, as noted in the well-known phrase, correlation does not imply causation, there is a distinction between these two concepts. One of the examples is Simpson's paradox. According to the left graph, it seems that exercise causes higher cholesterol levels as they are positively correlated. However, closer examination reveals a hidden confounding factor, age, which influences both exercise frequency and cholesterol levels. After dividing subjects into different age groups, we can observe that exercise decreases cholesterol levels. The impact of confounding factors is typically controlled by experimental approaches that involve random assignment of subjects to control and treated groups. Previous studies have also supported self-experimentation, an experimental approach wherein users engage in experiments on themselves. However, there are several limitations for conducting experiments in practice. Basically, most data in personal informatics is observational data collected in natural settings without predefined experimental conditions and corresponding random assignment. In addition, experiments are available only when manipulating conditions is readily achievable. From the user's perspective, always adhering to the randomly assigned conditions may increase user burden. Therefore, we aim to design a personal informatics system that supports users in exploring causal relationships through an alternative, quasi-experimental approach. As a case study, our system supports users to investigate contextual factors causally linked to perceived stress levels using self-tracking data. As discussed earlier, random allocation of subjects is crucial in the experimental approach, ensuring that any change in outcome is likely attributed to the treatment. However, in quasi-experimental studies, there is no random allocation, and external factors like confounding variables can influence the analysis results. To address this issue, we implemented matching, a technique that pairs subjects with identical combinations of confounding factors. Let's assume that different shapes represent different confounding factor values. In this situation, we pair subjects from treated and control groups if they are identical in the confounding factor, and create groups composed of those matched subjects. This process balances the distribution of confounding factors between the two groups, ensuring that any difference in outcomes is attributed to the treatment condition. Here is an example of how we actually implemented a quasi-experimental approach in this study. Let's suppose that someone has a question like, could studying be the cause of my increased stress? Then we may compare stress levels when studying versus not studying. However, as external factors such as friends, cafe, and late nights may influence the relationship between studying activity and stress levels, they should be considered in the causal analysis. The analysis begins with the data collection process. In this study, we employed the experience sampling method, sending a short survey to capture the user's context and stress levels at the time of responding. For each ESM survey, users reported their place, activity, and social setting as their context, along with their stress levels using a 5-point Likert scale. The response time for each survey was automatically recorded and also considered as a contextual factor. Then users were allowed to create groups of contextual factors based on their similarity. To implement a matching technique named Coulson exact matching, instead of matching samples only when they are exactly identical, this method allows matching if samples are similar enough, adopting a more relaxed approach. For this approach, it is necessary to first determine which samples are considered similar. For instance, if users collected data on 7 contexts for the place type, they grouped those contexts into 3 place bins, for example. Then contexts within the same bins were considered similar enough, allowing for matching even if they were not perfectly identical. Then samples, that is ESM survey responses, are assigned to treated or control group, depending on whether the activity is studying or not. After that, the samples are allocated to subsets based on combinations of user-defined bins. If we have 3 bins for each context type, a total of 27 subsets will be constructed from the combination of those bins. As illustrated in this example, samples within the same subset can be either identical or similar enough. Then samples in each subset will be weighted based on their relative proportions. Samples within the subsets exclusively consisting of treated or control samples will be considered unmatched and discarded during this process. Consequently, the samples of the 2 groups are balanced in their confounding factors, in this case, for the context of place, social setting, and time. Now we can compare the stress levels between the 2 groups to see whether studying really causes higher stress levels. For the user study design, a total of 24 participants took part in this study, all of whom were undergrad students from various academic majors. Also, on average, 566 ESM surveys were collected over 6 weeks. Moreover, we designed DeepStress, the personal informatics system with causal insights based on the findings from preliminary interview and literature review. DeepStress consists of 4 views: summary, calendar, context, and analysis. The latter 2 views are key to this system as they provide insights into the relationships between contextual factors and stress levels, including both correlational and causal perspectives. In the summary view, a brief overview of user stress levels and stressful context is provided as a landing page. The calendar view provides both summary and detailed records about stress, enabling users to reflect on their stress history. The calendar employs a color-coded representation of daily average stress levels, utilizing a spectrum where level 5, the red color, indicates high stress levels. If the user selects one specific day, all the details within that day are displayed, including variations in stress levels throughout the day, and the detailed records collected through ESMs in a timeline. In the context and analysis view, stress information within a specific context is presented using colors and small icons above. The average stress levels in that context are illustrated using colors, and this is associated with correlation as this does not involve balancing confounding factors. The causal relationship after balancing is described using ice and fire icons, and the number of those icons denotes statistical significance. The context view shows stress levels within a given context and the relationships with other contexts. It presents the ranking of the chosen context based on average stress level and frequency. users can examine the distribution of stress levels and relationships with other contexts based on the frequency of co-occurrence. The analysis view illustrates the causal relationship between a given context and stress levels. In addition, it describes other contexts affecting stress levels within the given context. Participants freely utilize DeepStress in both lab settings and real-world scenarios and share their experiences. From their experiences, we could identify that DeepStress supports users in exploring their stressful context by helping them recall past contexts and stress states, identify truly stressful contexts, and consider relationships between multiple contexts. When interpreting and conceptualizing the causal results provided by DeepStress, two main cases were identified. First, when the causal insights from DeepStress are consistent with the user's existing self-knowledge, they reconfirm the stressful context and accept the results without doubt. However, if there occurs inconsistency, users hypothesize about the reasons for unexpected causal analysis results and evaluate alternative explanations using self-knowledge and subtracting data. During the one-week follow-up field diary study, users reported that they revisited the data-driven insights from DeepStress and planned their everyday with the aim of lowering their stress levels. In addition, they re-evaluated the results in situ and developed coping actions for stress management based on causal relationships. DeepStress assists users in exploring which contexts are causally related to stress using their self-tracking observational data. By employing the causal inference based on the quasi-experimental approach, it addressed the limitations of existing approaches such as correlation analysis and self-experimentation, and bridges those two approaches to provide analysis with varying rigor levels. Moreover, the overall process of exploring causality in DeepStress can be interpreted through the Sensemaking framework. In the framework, user behaviors are divided into habitual and sense-making modes depending on whether new information has a gap with existing knowledge. These two modes were discovered in the DeepStress study as well. Also, the overall process can be explained through the data frame theory of sense-making. This theory explains how individuals make frames, or a mental model, based on the data or individual events, and revise the frames. Basically, when there is no gap between the existing self-knowledge and the causal results, the data frame relationship occurs only in this part. However, when a gap arises, another round of data frame relationship occurs between the raw data and the inferred causal relationships. Users further go over the data, evaluate whether the frame makes sense, and then reintegrate the frame with their existing knowledge. From this sense-making process, we suggest that personal informatics should be carefully designed to assist users in understanding and interpreting causal relationships, especially when they encounter unknown aspects about themselves. In this study, we show that personal informatics system can be enhanced by providing causal insights through quasi-experimental approaches, enabling users to employ their data in health management. At the same time, we suggest that HCI research should continue to investigate methods for users to easily understand and utilize data-driven causal insights. Thank you for your attention.